Hello everyone, welcome to Analog Circuit Design. This is Lecture 8, Common Source Amplifier. Also, I'd like to acknowledge my PhD advisor, Michael Flynn, and also a good friend of mine, Seung-Jung Lee. And this slide shows our class status. We're here, amplifier, common source. And here's today's outline. We finally learned about actual circuit amplifier. This is like the most basic amplifier. And then we'll learn about 4 types of its load. Before learning the actual amplifier circuit, maybe it's good to know what is amplifier and then where do we use it. Um, so actually, I think when you do an analog circuit design, it's like you always have to do amplifier circuit design. I would say like 80% of the analog circuit design is maybe amplifier. So every circuit has amplifier. Like for example, ADC, analog to digital converter, they have tons of amplifier. Amplifier is a key component for the ADC, or maybe DAC, or PLL, which is making clock, or power management IC, LDO, buck converter, boost converter, buck boost converter. So they all also have amplifier. So just every analog circuit has amplifier. And then I brought this figure from Razabi book. This is about RF transceiver. RF transceiver, this is like very general form and then is widely used. For example, when you do in your cell phone, in your smartphone, you have antenna. Every smartphone has antenna. And for maybe you use this for Wi-Fi or 5G. So for example, here antenna, they're getting like very high frequency. Maybe 5G, I think it was 20 to 30 gigahertz, some that range. And then the reason for, well, this is a side story, but reason for why using high frequency is first, we need to choose some data band, like frequency band. When I say 30 gigahertz of signal, it doesn't mean that the data rate is 30 gigahertz. It doesn't mean that. It means that carrier frequency is 30 gigahertz. Data is less than that. So when we say carrier frequency, the way how we transmit the signal is there's like a data signal, and then we mix it with very high frequency. So those actual signal in the air, they're like in very high frequency. As I said, because we need to choose a right frequency band because we don't want our frequency band is overlapped with the other applications. And then the other thing is that if frequency is high, we can make antenna very small. That's also a very important part. Well, anyway, come back to the amplifier. So the way how it works is that there's like in the air, there's very tiny signal, and then antenna catches that, and it goes to that's a receiver, right? Because we are receiving the data. So that signal goes to this way, the receiver path, and then you see there's LNA. LNA means low noise amplifier. We need low noise amplifier because the signal is really small. Assuming that, well, I mean, we haven't learned about noise, but we can understand it this way. The input signal is really small. If we have noise in it, the noise will just cover that input signal. So we don't want that. So that's why we need very clean, high performance amplifier for receiving the signal. And after that, there's down converter. Well, this is also out of our scope, but what down converter does is that they decrease the frequency. As I said, our data is on like few tens of gigahertz carrier frequency, but we cannot process on that. So we down convert that, and then now we are seeing a much lower frequency. And then those frequency goes amplified again, and like there's multiple amplifier, and then at the end of the day, there must be ADC, and then the digital circuit will go to our processor. You see, in our receiver path, there's already 3 amplifier. In my experience, we use more than this. There's a lot of amplifiers, and then we kind of tune the overall gain by tuning each stage amplifier. And then in transceiver, so transmitter is that we want to send the signal outside to the air. So we have our data is coming here, and then up converter. Now we have to increase the frequency. So up converter means increasing the frequency, and then PA, power amplifier. It means like strong amplifier. It consumes a lot of power. We put power because because it has to increase the power of the signal, and then we shoot the signal to the to the air through the antenna. So in this figure, they only draw like two amplifiers, but in real application, there's also tons of amplifier, row amplifier. So here, as you see, our very basic RF transceiver, which is a essential part of our cell phone, they have multiple amplifiers. We're going to learn about single stage amplifiers and this one. So I brought some figure from Rajabi book. What it says is analog design octagon. So as I said in the previous slide, amplifier is a buffer. We want to get a uh, small amplitude of signal, and then we want to amplify. Well, I mean, sometimes amplifier has less than one gain, but anyway. So amplifier is a buffer, and then when we design amplifier, we have to think about a lot of trade-off. For example, linearity, and so linearity means like here, linearity is a really important one. So ideally, we just want, if you put input, so amplifier looks like this. So X and Y, right? This is amplifier as a buffer. And what linearity means that if you put, I mean, just input and output should have a linear relation. I think we always want it. But in reality, X and Y are not in linear. You see that there's a curve. So this is a linearity problem. If you have too much gain, it's kind of hard to achieve linearity because, you know, we learned that the MOSFET operates in kind of small signal area. So if we change the MOSFET operating region too much, and then its characteristic changes. So, and it will cause a linearity problem. And if gain is too large, it's not good for that. And also, what else? Maybe noise and power. Usually in circuit design, if you want to reduce the noise, we have to consume more power. Also, if you want to reduce the noise, we usually need more size here. And then also maybe speed and voltage swing. It means that voltage swing is a like output, literally output voltage swing. If that's too large, we kind of have a slow amplifier, right? Because we have to touch those voltage peaks. Also, maybe like this one, supply voltage and voltage swing. So voltage swing is what we call as headroom. And in circuit design, headroom is really a crucial factor. And the reason why, like the analog circuit design in fine technology is difficult. Let's say like 20 um, let's say 28 nanometer. That's not that advanced, but anyway, 20 nanometer. I think. Well, actually, I used that 28 nanometer. The supply voltage is 1 volt. For 1 volt supply, it's kind of hard to design the analog circuit because due to the so we have to stack a lot of MOS, and then like for example here, like MOS, we're going to stack a lot of it, and then we sometimes when we design circuit, we also stack like lots of PMOS too. Then each of them require a certain amount of voltage, right? So it needs some voltage or voltage, and then also need voltage, and then also need voltage. So um, supply voltage is here, right? It's VDD. So if supply voltage is low, we have some trouble with voltage headroom, voltage swings. Yeah, so anyway, there's a lot of trade-off when we design amplifier, and then we'll focus on that. This is how a common source amplifier looks like. And so we're going to learn about common source amplifier, source follower, and common gate amplifier. So three of them. And then this is, among those three, this is the most like widely used amplifier. Let's see how it looks like. For example, here we have a V in input and then an MOSFET. Of course, this is connected to here. And the reason why we call this as common source means that the source here is grounded. So that's like our common reference. So that's why we call this as common source, as here, source and ground. And as we said, we learned about small signal model before. What it means? The assumption is that we have a large signal like DC bias voltage. So usually the V in looks like this. So there's like a AC source and like V bias, right? Usually it looks like this. And so when we do a small signal analysis, here, DC voltage goes to short. So we're going to ignore this. We will talk about this later. Anyway, the point here is that when we apply input to this amplifier, we have bias voltage and then AC voltage. So it looks like certain V bias, and then the input looks like this. Well, output also will somewhere looks like this. Maybe output will be here. So and then so this is VB out. And we have load here. In this case, in this example, we have resistor load. In this textbook, we're going to talk about like three types of load actually. So first one is triode. So here, triode PMOS. And then the other one is diode connected. This one has an interesting property. We'll learn about that. And then the other one is also a current source. This is also widely used. Let's focus on resistive load, RD. You see here RD. Maybe we can also look into the like operation region. So here operate in different regions. So what we did is assuming that the V in is, let's say, so as we said, there is small signal input, which is AC. This is AC. And then we have DC terms. So we'll just say VB. So actually in this graph, what we do is just change the V bias while the small signal V in, just small signal V in is 0. So that's what we did. Let's see what happened. First, if V in is too small, like this area. So what happened here? If V in, so we're talking about DC voltage, right? If DC voltage of V in is too low, let's say just 0 voltage, is this transistor turned on? No. So this transistor turns off. So there's no current, right? And what happened? If there's no current, this voltage will be just VDD. So that's why here's VDD. It starts from VDD. And then assuming that we're increasing the voltage, input voltage, as this MOSFET turns on, now it starts to flow current. What happened is that, so now V out would be VDD minus RDID, right? RDID. So if we increase the voltage more, the V out decreases. The V out decreases because the current here flows larger. And this region is saturation region. We need to think about it. Why? What's the saturation region condition? So VGS minus VTH is smaller than VDS, right? So VD starts from VDD, which is a very large value. So here the VD is maximum. So of course that's why it starts from saturation region, and once we increase the maybe certain part, and then let's say increase too much, then current flows too much, right? In this case, so this is actually V in minus VTH, and this is also um, sorry. So let's say this is V in some, maybe V in 2, okay? And this, do you know what this voltage is? This will be V in 2 minus VTH, because the output is actually what? This is VDS. And so after here, so this area, it becomes triode or linear region, right? Does it make sense? Because at this point, what happens is V in 2 um, minus VTH is VD, right? Because here. So they're at the edge. We discussed about the operation region, right? So this is cutoff, this is saturation, and this is linear. Of course, we're talking about M1's operation region. The important part here is that what area that we're gonna use. It's always here. We always try to make this as in saturation region. Why? Um, First of all, this part cutoff, we can't use it because this MOSFET is not working. So if whatever we do in Vin, VL will not change. How about linear? In linear, we learned about GM, right? GM, what was GM? GM was VID and then VGS, VGS, right? So in linear region, this GM is not large enough. So our like amplifier is not effective. Also, the other reason is that in this area, the current flows too much. So it's really bad. Just currents consumes a lot of power and then bad gain. So that's why we always use this amplifier in the saturation region. We talked about the operation region of this M1, M1. Let's focus on like the equation based about this DC bias. So here, large signal. This is important. Large signal means DC voltage. So DC is easy to remember it as DC bias. So what I'm saying is V out will look like there is some DC bias voltage and then the small signal. So if we apply small signal V in, and then of course this is also has its own DC bias, so it's like V bias, and then if we put assign a small signal in V in, then V out will have maybe a little large gain, but it also has its own bias voltage, right? This is what we call V out here as a large signal operation model. So V out is VDD minus what? The voltage across the RD, and we have a ID. We have our ID at the M1 MOSFET, so that will be RD times ID, right? And this would be VDD minus RD and 1 over 2 mu n COX W over L VGS minus VTH square. You know, this VGS is what? V in. This is not small signal input. Okay, this is important. This is large signal, which is V bias, okay? This is not small signal. That's the confusing part. What about in linear region? We also have linear region. Here, things are same, but we just have a different equation of current. So, again, large signal operation region means we want to find the DC operating point. I will say, okay. DC operating points. Okay, this is very important. Whenever we design circuit, we start from DC operating point to make our MOSFET in saturation. As I said before, we want this MOSFET as in always in saturation. This amplifier, M1, is always in saturation. So we can kind of also calculate the linear boundary by using some equation. The way how we do is that V in, let's say that's a boundary. We in the previous graph we said here is VTH, and then here is V in 1, right? And here is saturation, here is cutoff, and then this part is linear. So our target now is we want to calculate this value. How can we do it? So that will be V in 1 minus VTH, which is V out, right? This is V out. This is our V in, right? Because in boundary, their voltage is the same. Well, this is VDS, okay? So if you just calculate it, we got this equation. Here, this equation. We actually can solve this equation maybe by using some program or MATLAB or whatever. So we can get a V in actually. Let's calculate the gain. So there's like, I guess there's some, now it's small signal gain. So there's just back and forth sometimes. I mean, right before we talked about large signal, but now we suddenly talked about small signal. So I know this is confusing, but the way we can understand it is when we talk about large signal, it's usually we're just talking about operating point, DC operating point. So at that time, large signal means we're dealing with DC. So here, large signal. When we talk about large signal, it's about DC point. Okay. When we talk about small signal, this is AC gain. Okay. So here we're talking about small signal gain. So let's bring this equation again here, right? Where did we get this? Is it from small signal or large signal? This is large signal. How can we get a small signal gain from large signal? What we can do is get a derivative, right? So even though this is DC signal, but I mean, so small signal is just kind of a like give a excitation across the DC. So what I'm saying here is that so small signal is actually, let's say we have a DC operating point, it's V in. Let's say V in DC, and then with this V in, we also got V out, right? If we give some AC signal around V in, then V out will also move, and then we can derive that from this equation too. So what we're doing here is that we just will differentiate this equation, and let's just do a calculation. VDD is go out, and let's just ignore channel length modulation. But at the end of the day, we must have to care about this, but it usually can be also ignored. But usually we don't ignore it actually, I think in real design. But in this case, let's just ignore it. And then if you do this, it will be RD times, oh, so there's V in, right? So it will be just mu n COX W over L and V in minus VTH. You see that this is GM-RD because this is GM, right? This is GM. This is very, very basic equation. You're gonna use it all the time. So in different notation, we usually say AV, and then V is voltage gain, is minus GMRD. So this is equation-based approach. We starting from large signal equation, and then we differentiate it, and then get a small signal gain. So the other important part, I think, would be sign. This sign is always important. So this is minus sign. Why? Of course, we can show them in equation 2, but if you just intuitively think about it, what happen if we increase V in? If we increase V in, the current will increase, right? The current will increase. What happens if current increase? There's more voltage drop, right? And then the V out is VDD minus RDID. If there's larger ID, then V out will decrease. So they're operating in opposite. If we increase V in, then V out will decrease. Now we're gonna calculate the same small signal gain, but from small signal model. I think this is more important than getting a gain from the previous large signal equation. So um, let's do this. Let's draw first the small signal model. It should be V in, and so here plus minus V. This is just VGS, and here's a GM VGS, and we also have RO, right? This is now we're gonna talk about channel length modulation, and then we also have GMB VBS, and then here will be ground, and then there will be RD. So this is our small signal model. This is very important. You have to you can just throw it right at just right away. What I mean is that you have to really used to it. I think there might be one thing that you guys are confused, is that, oh, RD, wasn't it VDD, right? But why suddenly it becomes ground? Do you remember when we do small signal model, DC voltage will go to 0, right? It will be 0. I mean short. So basically what it looks like here is that like this, right? So this is VDD, but we just want to make it short. So now it becomes ground, okay? And the other thing will be this is a body effect. Do we have body effect here? No, because VBS, so here this is connected to the body, connected to ground, so we don't have it. So let's just remove it. So this part is what we have. Be very used to it. Be very used to draw a small signal model. What we draw looks like this. So I brought this figure from Razavi. It looks a little bit different. You know what's different? RD was we drew it like here, right? But since these are ground and everything is just ground, so this is same. And then you may wonder, oh, this ground, this RD ground, isn't it VDD? So can we, is the original VDD, can we just still consider it as ground? Yes, we can just consider it as ground. So they're just all same ground. We call this actually AC ground, okay? It's like in terms of AC, they're same. They're just not moving. Because basically small signal model is kind of differentiated version of circuit. Anyway, let's calculate the ground. I mean the gain. So there's some comment here. Often can ignore channel length modulation since R0 is larger than RD. But I would say in like a real circuit design, RD is not that small, because if RD is small, then we're consuming a lot of power. So um, usually we're not ignoring R0, RO. But here let's just calculate the gain. So what is the V out? So okay. AV was what? V out or V in. This is right. And then what we can do is we can just use a KCL. Okay. So let's calculate the gain using KCL. So use KCL. What we can do is let's look at this part. Okay. So GM V1 equal, so the currents from here. I mean, in Wasabi, they write it as capital, but I personally recommend to write it as small signal. I mean, lower signal, lower, what was it? Lower letter, not capital. So um, the KCL, the current here is the sum of so okay, if you use KCL, if you add V out over R0 plus RD, oh no, where's V out? RD, R0, right? This is KCL because the current from here is they're like, if we add them because they're sharing the same node, it should be 0. So if we just calculate it, GM V1 plus V out 1 over R0 plus RO. And if we just calculate it, so this will be V out minus V in, because V1 is V in, is actually minus GM RD parallel R0. Okay, so let me just write it down here again. So AV is minus GM RD parallel R0. I'm RO. You may wonder how we can get this. So RD parallel RO is, this is RD times RO, RD plus RO, right? This is actually looks like this, RD plus RO1. Okay, so whenever you see this, it's a good practice to brought up this one. Here, come back to the gain. Our gain looks like this. But if our RD is small compared to this R0, I mean RO, then we can just make it like minus GM RD. Okay. I think this is very basic calculation. I hope you guys are very used to this calculation. Maybe practice, or also in our in-person class, we'll practice a lot of this. We calculated the gain in the small signal model, and then we got this, right? What was the condition? Only when RO is a lot larger than RD. And then we can also represent the GM like this. You know how we can do that? So ID was 1 over 2 mu n COX W over L of VGS VTH squared, right? And then what was the GM? GM is ID. So GM is, like if we move V in, and then how much current that we can change. That GM, transconductance, right? So if we just do a calculation here, mu n COX, W over L, and then VGS minus VTH. right? So if you just compare these two, they're actually the same, right? If you ID is here, and then if you multiply by 2, and then if you just multiply it again, and that will be the square of GM. So maybe we can just use that and then see how can we get a maximum small signal gain. So AV was minus GM RD, right? But let's just use that GM term. So it will be over 2 mu n COX W over L, and then ID and RD. And then here's some trick. We're going to assume, so this is assumption, assuming VRD is constant. So VRD is here, VRD is ID RD. So I'll just say it V out. V out bias, V out DC point is constant. You know why we can assume V out is constant? So usually when we use this circuit amplifier, there comes the following circuit, right? So this operating point is it's like critical for the next circuit. So if we tune, let's say if you tune this circuit, it's kind of we just have to keep this as a constant because we're having the other following circuit. So this so so assuming V out DC point constant is in kind of a circuit system design point of view. Okay, so we are assuming DC point is constant. That means VRD is constant here, right? VRD constant. So this equation can be minus 2 mu n COX W over L, and then ID, and then, oh no, not this. And then RD is what? ID over VRD. And this can be over 2 mu n COX W over L, and then here VRD square ID. So how can we increase the gain with this? Again, the condition here is that everything is constant. You see that this is constant, but because this is just a like a design variable. So here, the maximum gain I'm saying is that when the this M1 is constant, constant size. Okay. So what we can change here is only this ID. So here's our equation. So the way we can, assuming that everything is just fixed, and then there is only IDs, what we can change, well, actually ID and RD. Then if you want to maximize the gain, so minimize ID. So we need to decrease our ID. But as I said, VRD was ID and RD. If we decrease it, and then we need to increase RD, right? And then again, here VRD is constant, as I said, because of the following circuit. Usually there is a following circuit, and then the operating point of V out is important. So we just keep VRD constant, assume. So here, to maximize the gain, we have to reduce ID and then increase RD. But the problem here is that this is very slow. So you know why it's slow? Assuming that there's a load and something like capacitance is there. And then the current, actually this ID current, and then this RD is kind of making a, I'm saying about small signal. They're kind of making a RC constant here, right? But if you have large RC and then here's RD. If you have large RD, the current flows here is small, so we kind of have a hard time to change the voltage here, right? So that's why we said the circuit is slow. In practice, so we usually don't use a resistor load because low gain. Why? So what's our gain? Our gain is here. Here. Our gain is here. If we want a large gain, what do? We need to increase RD. But it's hard. Um, resistor is really big in chip. Um, it's literally like a poly, the bunch of poly. So the reason is a resistor, I mean on chip, is too large in area. So that's a problem. That's why I said before we assume that R O is a lot larger than RD, right? Because we cannot make this RD too large because of the area problem. And then that's why I said these are RO is usually not ignored because we're not using this RD as I mean, resistor as a load. So there's the other way to do that. I mean, there's also like cascode but we'll learn about that too again. So anyway, the point is that in real circuit, we are not using actual resistor as a common source amplifier load. Okay. Next one, we'll treat about this triode region MOS load. Oh, but in previous slide I said to increase the gain, I said we use a cascode. That's also true, but we also use this current source. This is also give us a large gain. But let's focus on triode region MOS load. Let's talk about triode load. I think these are just basically the same. We're kind of using a resistive load. The difference is that in previous we actually use a RD, physical RD, but now we're using transistor, which is PMOS. So PMOS, because this is in triode region or linear region, we have our own resistance, right? But note that this is PMOS, okay? So let's draw it larger. So here VDD and here VB. So this is PMOS and then here's Vout, right? So we want to make this in triode region. So what voltage Vout should be? So assuming that there's VTH-P and this is usually minus, right? So assume that this is 0.8 volt. And assuming that VDD is what? Maybe 1.8 volts. Then can you tell what's the level of Vout should be? First of all, we said this is um, linear, right? Or triode. To do so, if Vout should Vout large, should Vout high, or should Vout low? Um, this is important. Vout should be high, right? Because here is source and here is drain. So to make the transistor in MOSFET in linear, VDS should be small. So here in NMOS, VGS minus VTH should be larger than VDS. So that's like the condition for NMOS triode. This is the same, so we just need a small Vout. So Vout should be actually, let's calculate the VGS, PMOS term. Oh no, I just want to use black color. Here VGS minus V Um, well, okay, we need a value for this VB2. Let's say VB is, because VTH is here, let's say like 0.8 volts, okay? So what's the VGS now for PMOS? I'm just gonna use an absolute value. Um, so this would be 0.2. Oh, no, 1 volt. Actually, this is 1 volt. This is 0.1 volt. And then so our VGS minus VTH is, so VGS minus VTH is, this is also absolute value. So this will be 0.2, right? So in this case, to be a triode region, um, so V out should be higher than 1.6 volt. Does it make sense? This is kind of confusing, right? So try to calculate it. I think this is a really good exercise for you. Try this and then get a V out operation region. So again here, as I said, we need a high V out to make this in triode, and then so V out should be higher than 1.6 volt in this case. Okay. To calculate the gain. So this is the same, right? Because we try to just model this MOSFET, this PMOS as a just R1 on resistance. So this would be just minus GM R on 2. And then in our triode region, we learned about this equation, but I'm just gonna wrote it down. So we PCOX and WL over 2. I said this, I mean WL for MOSFET 2. So this one is M2. Okay, M2. And then here VDD minus VB minus VTHP. So I think the confusing point is that the polarity of VTH or whatever. So one thing that I would suggest you to do that is, so actually VTHP is minus voltage, right? Let's say just 1.8 volt or something. So and what is VGS? VGS is V gate minus VS, and then this would be VB minus VDD, right? So these are like, you see that the sign is all mixed up, but again, the point here is that this should be larger than 0. So try to adjust the sign, and it turns out it looks like this. Is this circuit good? No. This circuit is not good because first reason, VB. I mean, how do we like set the VB? It's kind of, I mean, set VB is very difficult in practice. And then also it's kind of must compensate for PVT variation, and also this is the most, maybe the biggest problem, gain still low, because in linear region the transistor is fully turned on. I kind of operate as a switch, so this R on 2 is not that large. And then like this 2, you may wonder what it means. When you see this R on 2 value is just decided by like some absolute parameters, right? So for example, with this VTH. Oh, by the way, PVT means, so PVT means process voltage and temperature. In process, we say like TT or FF or SS. So it means like how fast the MMOS is, how fast the PMOS is. So as I said, even if we are using, let's say we're using like 180 nano, every silicon wafer is different. Like, because we do a lot of doping and then, so there's so much variation. Some PMOS, for example, for FF, here FF case, the NMOS VTH is really low. So for example, here in FF case, VTH low, SS VTH high, something like this. Voltage, voltage can be maybe, let's say 1.7 volt or 1.8 volt or 1.9 volt, because in reality, in practice, we're not using an ideal voltage source. We're using some LDO, buck converter, or something like that. So voltage always varied. Temperature, this is really huge. This is more like hard problem. Maybe something is operating this, or maybe something is operating this. The reason why temperature is the hardest is that this PV, we can kind of do a calibration. Okay, we can do calibration. So for example, this process, once silicon is fabricated, process is fixed. So we can deal with it. But temperature is not. Temperature changes all the time. That's why temperature is kind of hard. So when I was in company, dealing with temperature variation is, I think it's hard because we cannot do any calibration here. So anyway, so this VTH or maybe even the dimension, those things are kind of absolute values. So which means it's not a ratio, it's absolute value. That means it's vulnerable to PVT variation. So long story short, what I'm saying is to control this R on to, controlling in R on to value is difficult. So we're not using it, but for most reason gain is low, so we're not going to use it. So far we learned about two load. First one was the resistor, and then the second was triode. So now let's talk about diode connected MOS load. Diode connected load means, so this is an NMOS diode connected load, and we also can have PMOS diode connected load. So what we'll do is that we want to replace this resistor load with our MOSFET. So as I said before, actually this is not some, this is in, I would say, all CMOS technology. It is difficult to fabricate resistors with tightly controlled values. It means that it's really hard to get a absolute resistor value and or like a reasonable physical size. So if you want to make a resistor big, the resistance high, then it requires a lot of area. So that's not good. We're gonna replace our resistor to MOSFET type, and then one way to do that is diode connected load. The reason why we call this as diode is that when we think about this BJT, we're maybe connecting these two, B and C. So base corresponds to gate in MOSFET. So if you connect this, it looks like P to N, right? So what is diode? Diode is P to N junction, right? And if we also let's say, so we have diode connection here. And then let's say we are place some Vx and then let's say Ix, and then this is NMOS. So if we go to Vx, I is suddenly increased. It's like this. So it's because VGS, so it's like this. And it's kind of looking like a diode because, the ideal IV curve of diode is just this, right? At the at the VT threshold, turn on voltage, the current just suddenly increase. And this NMOS, the current is not like dramatically increased, but still we have a VTH here, and then the current increase at the with a square low. So again, the current profile of this diode connected load looks like diode 2. And this is important, always in saturation region, because so what was the saturation region condition? It was VGS minus VTH is smaller than VDS, right? But now VGS is VDS, right? So, but in this case, VGS is VDS in diode connection. So this condition always satisfy, because if you just remove this, minus VTH is less than 0. So this is always in saturation region. Even though the load is diode connected MOSFET, the way how we calculate is the same. So do you remember in our gain? So the gain when the load was a resistor, gain was GMRD, right? So the same, we want to kind of calculate the equivalent resistance. So this is what we're doing. This is a diode connected load, and we want to calculate, we want to measure the resistance, input resistance, so like here, R in. To calculate that, we're going to use this small signal model here. And since this is NMOS, we can represent it like this. And then note that we also have VG body effect, because the source voltage here, the source voltage and body voltage are not the same. So our goal is to calculate the input resistance to this node, because as we said, what we're doing is here's the NMOS, and here's the input NMOS V in and then V out, and we want to calculate the resistor here, because our goal is we want to get a gain which is GM1 and R. Well, just say RD. So the way how we can calculate is R in is IX over VX, and then I'm gonna use a KCL at this node. Okay, so IX is the sum of minus GMV1, because this current should be the sum of this, right? And then so Vx RO minus GMB VBS, and V1 is minus Vx, right? They have a opposite sign, and VBS is VB minus VS, and then VB is 0, because the NMOS bulk is connected to 0, and then VS is also VX, right? So if we just substitute this to here, it turns out IX is Vx GM plus 1 over RO plus GMB. And so Vx Ix would be 1 GM plus GMB plus 1 over R0. This is what we got, right? And actually we can represent it as like this. So this is a very useful form. It's like so GM over 1 over GM is its order is resistance. Okay, this is also 1 over GMB is also resistance. So when we do a like parallel resistance connection, it will looks like it will look like R1 over R2. So this is R1, R2, right? And this is also R1 plus R2 plus R3. This is R1, R2, R3. Okay. Yeah, so it's like parallel connection of R1, R2, R3. So this can be look like it will be look like this. And then since RO is usually a lot larger than GM, so we can just simplify this. Now let's calculate the gain. So here, what was the gain? Gain is minus GM1 RD, right? So and then we calculate RD as this. In here, we are ignoring 1 over GM, R0, or actually it's like GM plus GMB is a lot smaller than R0, and this is usually true in CMOS technology. So the gain would be here GM1 times RD, and then again GM1 is the transconductance of this M1 NMOS, and we can write it down like this, and it will be like this. So because the GMB, we assume that GMB is eta GM2. Okay, so we can get this kind of equation, and this gives us this has some interesting characteristic. We got a gain equation, right? We got a gain equation here, and then let's kind of modify the equation. As you remember, ID is 1 over 2 mu n COX W over L VGS minus VTH. We're ignoring body effect. I mean channel length modulation. Again, this equation is really important. Must memorize it. And GM is ID VGS derivative, and this is also mu n COX W over L ID. You can easily derive this equation. So if we just substitute it here, let's just substitute it here, and then we got this. We can make it even simpler because what was our circuit? So our circuit is like this, and so here NMOS V out. So the current ID1, ID2, and ID1, they are the same, right? So we can remove this. So we got this. And then if you also, let's say, just ignore body effect, this will be just, well, I mean, if you just ignore body effect, then it just go out, right? This equation has some interesting characteristic. So AV was WL1 and WL2, right? This is when NMOS and NMOS, right? But in PMOS, we can also repeat the calculation, and then you can easily show this equation. So the difference would be just this mu n and mu p. So as I said, this equation gives us some interesting characteristic. What's the advantage? So when we see this equation, the gain is just function of dimension ratio, dimension ratio, right? This is good because, as I said, there is PVT variation, right? It means if we, let's say, if you have 1k ohm resistor, right? This is not actually 1k ohm. It depends on the PVT variation. Okay, just so let's say resistance is 1 kilo ohm, but because of PVT variation, it can go to maybe like 1.3k or even like 0.7k. So if we use resistor as a common source amplifier load, our gain is kind of not stable. But um, this one is kind of, this one is not a function of variation. So what I'm saying is the ratio of dimension, they're like very immune to PVT variation. So these are just constants. For example, um, if let's say W and L, so W1 actually becomes like 10% larger, so it becomes 10% larger W1. But what the good point is that W2, that's also become 10% larger because in layout, those two MOSFET are really close. They're placed by really close in terms of layout. If they're close in terms of distance, it's highly likely their performance, like their MOSFET parameters, are very similar. So I'm saying if the width becomes suddenly 10% larger, then the other width will be also 10% larger. I mean, well, 10% is not a realistic number. It's not that bad. But anyway, the point here is that the ratio is always a good way to design circuit. So for example, we also use like resistance ratio or capacitance ratio, something like that. So when we put ratio there, it means that it's kind of very immune to variation. So that's an advantage. If we draw draw the like layout well, our gain is kind of constant. So it's like immune 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 to PVT variation. I mean gain. Gain is immune to PVT variation. Then what would be the design disadvantage? It's about one disadvantage is um, like swing. If you want to get a large gain, then voltage swing is a problem. Why this diode connected load has a voltage swing issue? Our gain would look like this, right? We already calculated, and here this equation is from ID2 equal ID1, and ID2 is here, ID2, and then this is ID1. So they should be equal, right? Because, well, I mean, they share the line. So that gives this equation. And then if we substitute this to here, so if we put it here, and then we get this equation. So it means that to get a high gain, to get a higher gain, we need to increase the V overdrive of PMOS. For example, let's say this V overdrive is, let's say, like 100 millivolt, and then we want to achieve like gain 5, then we want this as 500 millivolt, right? So, and maybe let's say our VDD is 1 volt, and VTH, and in this case, so if VDD is 1 volt and this kind of 500 millivolt and then 100 millivolt, it will give us a very small output swing at the V out, because this is already consumes here, right? Here, let's say, for example, um, VGS2 minus VTH2 is 500 millivolt. And then assuming that VTH2 is, let's say like 40, 400, 300 millivolt, 300 millivolt. It gives us that VGS2 should be 800 millivolt. So here, in this situation, this is G and this is 1 volt because VDD, and then this is S, right? So it means that this voltage is already like 200 millivolt, right? So that's how here minus plus 800 millivolt, right? So our VDD is 1 volt, but the output bias is already like 200 millivolt. This is kind of hard to use, but because its voltage is too low. So that's what it means to get a high gain, to get a high voltage gain. A large VOV is necessary. So that's an issue. So with this kind of with this diode connected load common source amplifier, it's hard to get a large gain. And the other issue would be for a high voltage gain. What it says is so AV, AV is in the above UP and W1 and WL2, right? And assuming the UN is mu 2 mu p, so it's like mobility. Usually the mobility of electron is better than the mobility in PMOS. But in like very advanced technology, this is also different. But just assuming that like a normal technology, electron mobility is good, better. So let's say we want to get like 5. It turns out 25 mu n mu p WL and W over L 2. And then since this is 2, it turns out it give us 12.5 WL and WL1 L2. So what it says is W1, the NMOS size. Here NMOS 1 size should be 12.5 larger than PMOS size. So when we draw layout, the layout looks like this. Layout will look like PMOS, very large PMOS, or NMOS here. So layout is kind of weird. Or well, actually we can just use maybe fingers, so maybe we can draw like this. But still, these unbalanced layout is like not favorable. So that's also the other issue. The last type of load is current source load. So basically, this is what we use usually. This is like the most widely used. As I said, in the diode connected MOS, the gain is represented like the ratio of dimension, and then so the gain is like ratio of dimension. So as I said, this is good because we can kind of get an accurate gain. But in reality, usually what we want is just high gain. But in reality, important part is we want high gain, like very high gain, and then we'll use some feedback so we can get some like accurate operation. So again, for a diode connected MOS load, its gain is the ratio of dimension, so it's immune to PVT, but it's not that useful because in actual application, what we want is high gain. So for that high gain, we will use this current source load. This schematic shows our common source amplifier with current source load. Okay. Now we need to calculate gain, right? To do so, let's use a small signal model. Small signal model. Well, we know how to change the NMOS, right? So these are NMOS small signal model. Then how about this current source? How do we change it? So the answer is we're just open it. We assume that there's nothing attached. Just open. And let me explain why it is open. Um, let's see for current source here, and let's say we want to calculate the small signal resistance, because when we change a circuit to small signal model, we're only focusing on its like a differential version. We're not considering the DC version, right? Because DC type, they just set the operating point, and then, like for example, they are kind of setting this GM. So we want small signal resistance, and so the way how we calculate is, so let's say Vx becomes Vx plus delta Vx. So this delta Vx is kind of a small excitation, and Ix will be Ix plus delta Ix, right? Delta Ix. So what we want is, let's say Rd. This is for small signal. Is delta Ix and delta Vx, right? But this is current source. Current source will not allow any change of current, right? So what actually current source does is, so if we change the voltage, no matter what, current source always supply the same current. So it means that delta Ix is always 0. So Rd is actually, we assume that this is infinity. Okay, our small signal Rd is infinity. That's why we replace the current source as an open node. Now let's calculate the gain. So we learned that current source will be open node, and it's kind of easy to calculate it, right? So the gain would be minus GM times RO, right? In this case, this RO is from channel length modulation. From now, we cannot neglect RO anymore. So as I said, circuit design is kind of it's a lot of approximation. Before we could have ignored the RO because we had some like RD here, right? In our previous case, we had RD, and RD was a lot smaller than RO. So RO parallel LD is just RD. That's why how we ignored our RO before, but now we cannot. So since we don't have it, we cannot ignore RO. And this is also called as intrinsic gain of, let's say, MOSFET M1. What it does is that this is the theoretical gain that this M1 MOSFET, the maximum gain that this M1 MOSFET have. If we put like the ideal current source, then this would be the like a maximum gain that this MOSFET can achieve. So we also call this as intrinsic gain. But something's weird here. So how does MOS works? So if we put some small signal in V in, then the current of M1 changes. That's what we learned, right? Because the current changes like this GMV in. So, and then current here, but we have current source. We have current source. So the current through NMOS will not change. So how can we make V out fluctuate, V out like work? Because we don't have any current change. So actually, the way how it works is that current is not changing. That's true, but VDS is changing. So when we see this current source, I mean current equation, if we change V in, right? So let's say if we increase V in, but this one is constant by current source. So if we change V in, then V out must change. V out must goes down, right? That's how V in, the change in V in translate to V out change. So again, currents are the same. Current does not change, but we can still make the V out move by this equation. So if we increase V in, since the current is always the same, the V out automatically goes down. But in real life, do we have ideal current source? No, the ideal current source doesn't exist in real life, in real circuit. So what we do is we actually replace this current source with this PMOS. This is a very basic way to implement it. So we learned about like triode region load, but this is different. This must have to be in saturation because we on current source. Maybe I can repeat why the saturation MOSFET operates like a current source, because when we see the IV curve, so this is VGS. Oh, actually this is not VGS, this is VDS. If we say VDS and then ID, so in an ideal MOSFET looks like this. So here is saturation. Well, actually we do have some slope because of the channel length modulation lambda. But basically in saturation region, the current is not changing that much. And then that's the definition of current source, right? The definition of the current source means even though we change the voltage across the current source, the current is not changing. So this MOSFET in saturation region is kind of non-ideal current source. So we have to put this M2S in saturation region. And then now let's calculate the gain. So let's draw a small signal model. So for V in, plus minus, and here's V in, right? And here we have GMV V in and RO. Now we cannot ignore RO, right? Then how about this PMOS small signal model? So the polarity is kind of tricky, but here's how you can do it. So let's just draw a current direction like this, GM2 VGS, and absolute value, okay? And then the other thing would be R02, and so here is actually, so just say plus minus 1 VGS, okay? Because the upper side is, I mean, it was in VDD, right? So just you can say like this, and this VB. So this is actually ground because this is DC voltage. So this is just DC bias. In small signal model, DC voltage source becomes shorted, right? So it becomes ground. And then same as VDD. So VDD becomes also ground. Since here VGS is 0, right? I mean, small signal VGS is 0. Okay, the actual VGS, I mean, large signal VGS, well, of course, it's not 0. Large signal VGS is VDD minus VB, right? But we're talking about small signal VGS here, and then this is 0 because both of them are just DC. No change in small signal model. So it becomes, we just ignore this, and we only have R0, R out 2, and R out 1. And then you see that there is also ground, and here is also ground. This is also ground. So this turns out to plus minus V in, GMV in, and here's R01 parallel R02. So the gain is minus GM1 and R01 parallel R02. This is our answer. The other thing maybe we can look into it is this V bias. How do we set this voltage? So we're going to use a current mirror. So actually this is decided by, I mean, supplied by current mirror. We'll learn it in like a later lecture.